We have quite a few people joining us this morning, evening, afternoon. So thanks so much for joining us for our next expert lecture with GoAERO. As you know, we're so pleased to have our partners, Boeing, NASA, RTX, Honeywell, Iridium, Global Aerospace, and SAFT with us, as always, along with our 30 plus organizational partners from around the world. And today we're so pleased to have Khushin Lakhara here from MathWorks. He'll be lecturing about accelerating aerospace vehicle design for the GoAERO competition with MATLAB and Simulink. He is currently an aerospace engineer in the student programs team at MathWorks. He develops technical tools and content to design aircraft, UAVs, and flight controllers for aerospace student competitions. He received his B.Tech and M.Tech degrees in aerospace engineering from the Defense Institute of Advanced Technology in India, and he has previously designed UAVs, developed a flight controller for combat UAVs, and published research articles in the field of high-power electric propulsion. His major areas of interest are drone design, flight controller development, and mission simulation. Thank you, Khushin. We're so pleased to have you here today.
Thanks a lot. Thanks for the introduction. Hello, everyone. Let me share my screen. Good morning, good afternoon, and good evening, audience, from wherever the part of the globe you are attending this webinar. Especially for the GoAERO competition, either you are coming up with a fixed-wing design aircraft, a helicopter, or a hybrid. For all these aerospace vehicle, you need to go for the certification requirements. You need to get an airworthiness certificates, and this will go through some safety critical standard requirements. And one of such requirements is the DO178C. So now the question is, if you are going through all these requirements and throughout the design process, if you find that due to any reason, if your requirements changes, how are you going to deliver faster, meet changing design requirements, and going to ensure the quality throughout your design process? So here we are to address this, and in this webinar, we are going to discuss how can you accelerate the aerospace vehicle design with MATLAB and Simulink, especially for the GoAERO competition. Uh, so so today's agenda we would be discussing what is the model-based design approach, why do we need it, and what is it actually. Moving forward, we'll talk about how does the verification and validation approach of model-based design accelerates the workflow. And at last, we would be discussing about which are the tools using which you can perform model-based design for aerospace vehicle workflow. We will be also discussing how the MATLAB and Simulink helps you in complete model-based design approach. So you would be curious, like, where does the industry is using it? There are so many user stories out there where the industries are using model-based design approach, and they have developed the verification and certification of the DO178B and DO178C requirements, and developed their flight controller softwares, developed their airworthiness certification software requirements. So we are going to talk about that. With this motivation, let's start our discussion with why do we need the model-based design approach at start. So if we talk about how does the aerospace systems get built, we start with the concept of operations. We will be doing our research, and from research, we'll be coming up with the ideas that we should have X configuration, Y configuration, or we should have the particular design. Once these configurations based on our engineering research are finalized, we go for the system requirements. These requirements may be either given by the competition organizers, or in the industry, it may be given by your customers, or these requirements can be also formulated based on your ideas for competing for your score or competing for your competition. So once your requirements are finalized, you move forward and develop your system architecture, and accordingly, you develop your component design. You develop your component design, you implement your component. It may include developing your software as well, developing hardware, and finally, you integrate all these software, hardware, and various components to make the subsystems, and from subsystems, you integrate the system. Along with all of this subsystem and system integration, what major requirements come is the system test and verification, that finally you test how is your system performing, does it meet your requirements or not, and if it meets requirement, you're well and good to go for the launch, and then you then you go for your operation and maintenance things. So here for this discussion, we are not going to talk about ConOps and operation and maintenance, but we would be more talking about our design cycle starting from system requirements to system test and verification. So if we talk about the traditional approach, traditional design approach, it will have it traditional design approach. It includes continuously moving step by step, and it may have its own issues. So if we talk about some of the issues, uh, system requirements start with documents. So most of the time, system requirements are either in a Word document or it may be the ideas which has been captured into the documents and which are actually may be difficult to interpret. And also, the requirements which are in the documents, if you want to see their impact on your component design or on your code, it may not be quite easy task. Moving forward, once your requirements are there, you move for system architecture and go for component design. It includes developing your physical prototypes, which is actually expensive, and it also prevents you to do rapid iteration. And because you are developing the components, it does not give you an opportunity for the system level testing as well. So here you're designing the components, separate components, but until and unless your complete system is ready, you can't do the testing. If we talk about, especially about the component implementation, which includes the software development, you may be doing the manual coding, which is not only time consuming, but as the manual coding is based on the human skills, it may introduce defects and variants. And sometimes if the other people are using moving forward, it may be difficult to reuse as well. Finally, once our component implementation is done and we go for the system test and verification, what we see is at the end of the design cycle, we are finally doing the tests and verifications. And this actually brings the issues because throughout the design requirement, we have completed, and now we are testing if my requirements are meeting my design or not. If there are issues, we have to go through at the start of the cycle and do all of the analysis. As the design and integration issues found at the last of the design cycle, uh, it may cost you more. It also, if you want to fix all these issues, it's difficult to trace that which requirements it resulting in what issue, or what issue can be fixed by relieving what requirement. So there is no traceability with this traditional design approach. If you're trying to fix various errors based on a survey which was done by NASA in 2004, we see that the earlier you fix these errors, more the money you save. The later you are getting, the late you are getting, more the delay, more the cost would be increasing. So what is the solution in this case? Can model-based design help us to save from that? Let's explore. So at model-based design, if we talk about model is at the center of complete design process. You design with simulation instead of developing your physical components. You develop the models and you simulate, you analyze, you execute specifications from the models. And it also involves continuous test and verification. So it does not matter either you are at the system requirements level or system architecture levels, you are performing you're performing continuous test and verification. And it also gives you the capabilities such as automatic code generation. So if we talk about specifically how each of the issue is addressed in the model-based design approach compared to the traditional design approach, the system requirements, which in the traditional design approach is mostly in the Word documents or documented in Excel files or any other document, these requirements are actually modeled. So the requirement models has been developed, which actually gives you the traceability, which gives you an opportunity to formalize all your requirements. And even if later on, if some changes are coming up, it creates a digital thread throughout your design. So you can trace that if my this design point of design is changing, how my complete system or which subcomponents or which subsystems and components would be impacted. Uh, as the model-based design include the multi-domain design simulations, it saves you a lot of cost. You do not need to develop the expensive prototypes. It saves you from the manual coding because you can, instead of writing your own code, you are generating the code and deploying on hardware. And this code you can optimize as per your industry standards. So depending on which industry you're working and what safety critical systems you are developing. Accordingly, you can generate the code as per these requirements and implement it. So even at the component level, you are making sure that your components and the complete design meets the industry standards and requirements. Moving forward, in the system integration, you find all the in the system integration, you have the traceability. So requirements are fed or not, which requirements are meeting, what are the issues at every level, subsystem and system level. You are getting all this information, and you can correct them early instead of correcting them at final stage. So this continuous test and verification approach of the Simulink helps us a lot. Uh, uh, so now the point is like, what are the tools using which we can perform this model-based design? So can we do it using the MATLAB and Simulink? So if we talk about the MATLAB is a platform used by the engineers and scientists across the world to perform numeric computation, data analytics and visualization, algorithm development, and a lot of things. Uh, we got the MATLAB is used from the audio industry to the aerospace industry. Uh, it has its own programming environment. Also, it is supported by multiple GUI apps. So it's not just a programming language, but it's more than that. It's a complete platform which helps you to do a lot of modeling and simulations. Moving forward, we have Simulink. The Simulink is actually the model-based design. It's a block diagram modeling approach. So here, instead of coding, you have the blocks and signals which you connect, and you create the components, subcomponents, and then subsystem and this complete system. So this layer by layer approach helps you to take care of your model-based design requirements with more than 100 toolboxes and block sets. Simulink supports a wide variety of industries. Uh, so now you would be curious, like we talked about MATLAB and Simulink, we talked about the model-based design, but how the industry is using it. So Bell Helicopters developed their first civilian tilt rotor, and using MATLAB and Simulink that did it, and they could reduce their development by 10 to the 1. That was a great achievement for the team. Project development time was reduced by 80%. They could find all the problems earlier and eliminate faster, and they could meet all their certification requirements as well. Now, as we have motivated enough to about the model-based design, you would be curious, like how does the model-based design is actually accelerating the workflow? What is there which is doing it? If we talk in detail, it has a verification and validation approach. So how does it help us? Let's do a deep dive and understand that how the verification and validation approach, which we would be calling as VNV moving forward. So how does the VNV approach of MBD accelerates the workflow? So when we talk about the model-based design, it's actually the amalgamation of two things. One is the modeling, and second is automation. So in the modeling involves the simulation and analysis. So you can uh, develop your components, you can model all your physics using MATLAB, Simulink, and straight flows. You can do your simulations. Using the simulations, you can do a number of analysis and optimizations uh, and optimize your overall system performance. Once your modeling is done and you are ready with your models, moving forward, we had to integrate them with the hardware, and also we have to make sure that whatever work are working in the simulation is goes well with the hardware, and that's where the automation capabilities of the model-based design and helps you. So you can do the code generation instead of writing the manual code. You can deploy your code on the hardware, and with the software in the loop simulation and hardware in the loop simulation capabilities, you can actually do the real-time simulation and testing and found if there are any integration issues and fix them. Moving forward, it also helps you to model and code verifications and automating manual checks. So you don't need to do all the checks one by one. You can develop your custom guidelines for the models, and accordingly, using Simulink check, you can develop your check guidelines, which can be directly implemented on models. So by the time you are at the end of your model by the time you are at the end of your design cycle, you make sure that your system is meeting not only all the requirements, but it's optimized as well. So let's deep dive into and understand how this analysis and everything comes up. So if you look from the competition organizers or customers in the industry, they give us some requirements, and what they finally look for is uh, they want to see the performance. So they link actually the requirements to the systems and which is connected to the components. So this actually linking top down and bottom up workflows. But as a system engineer, what do we want is we want an abstract view which has the not all the details, but we can get an idea how my system is working. So for that purpose, you can use the requirement toolbox for modeling your requirements. Once your requirements are modeled, using the system composer, you can you can author complete system architecture and link all of your requirements to your system. And finally, in Simulink, model your you can model your plant physics or plant dynamics and various subcomponents and generate complete system level design. What once your modeling is ready, the systematic verification and validations are to find defects sooner and shorten your launch time. So this is the outline of the MathWorks model and verification approach, and our customers has reduced cost and project risk by the early verification by authoring and managing requirements in Simulink, automating manual verification tasks, and all of these capabilities are part of workflow which conforms to the safety standards. So when you are working with the safety critical systems in aerospace industry, it becomes very crucial that each of the safety requirements you embed in your design since starting, instead of completing your design and at last going for your certification process. So this system verification and validation approach helps us a lot. Let's move forward and understand this how each of the component of this high integrity verification flow works. So once your requirements are modeled, either these were text and or any other requirement capturing tools, we create the requirements models from that. And once your requirements are formalized and finalized, moving forward, we create implementation model. So this implementation model is mostly the modeling of your complete vehicle, your various subcomponents, your plant dynamics, all the capabilities that you want to capture in your system. You develop that, and once your implementation model is free of all the errors, run all the checks, and it also if it also complies with your industry standards, you move forward for generating the code. Now, this code generation can go on the hardware, which can be integrated finally on the hardware. And throughout this design process, it gives an opportunity to identify and trace that whatever the requirements we provided, how these requirements are impacting each of the part. So for all these purpose requirements, Toolbox helps us to uh, formalize and validate requirements using requirements modeling. So your requirements are conformed to the requirement models, and your requirement models are connected to the implementation models. These all the requirements modeling make sure that we are adhering to the standard compliance reviews and static analysis. You can use the Simulink check and Simulink design verifiers to make sure that all these things are working, and that's make sure that you go through the you takes care of uh, defining your custom check or your standard specific requirement checks. Once these requirements are done and you do the formal verification that your implementation model and requirements model are robust and meeting all the requirements, you can move forward and do your model in the loop testing. So model in the loop testing, it's mostly involved that, hey, my model involves all the checks and it's meeting all the defined requirements. These may be the design requirements or your industry standard requirements or your competition requirements. Once your model in loop is done, in the simulation, we can move forward for the software in the loop testing and processor in the loop testing and hardware in the loop testing. So this makes sure that whatever the code we generated, whatever the model we implemented, this is also adhering to industry standards, and generated code is also adhering to your industry standards. So once you perform that, actually you are ready to generate various tests and test your system performance on the system performance against various checks. So you can do that using Simulink Design Verifier and Polyspace Code Prover. So that's all about Simulink. So that's all about how the V&V approach of the model-based design helps you to accelerate the workflow. This is another user story where the HELA reduces their sensor development time by 60%. They model their requirements, validated and design verified months earlier than it was earlier process possible. They could also do the prototype incorporating 80% of product functionality produced within the months, which was earlier in the years. With this motivation, I know you would be curious that we have model-based design and V&V approach, but which are the various tools or how the various capabilities of MATLAB and Simulink helps you to perform this model-based design. So now we would be going through each part of our model-based design approach, starting from the system requirements. How does it help you, and what are the various tools you can use? So let's start our discussion with the system requirements here. So in the system requirements, as we discussed, that traceability is something very important. And the reason for the traceability important is that it ensures that your application is complete, fully tested, and meets all the requirements. And also, if you are making any changes, you should be able to understand that the component level change, how it will make the change in the how it can impact your requirements. And if you are making any changes in the requirements, what components or what subsystems it will impact. So you should be able to get the impact from both the side, from the requirements to the component and subsystem. And if you are making changes in components to subsystem, you should be able to see that how these would be impacting my requirements. So, and obviously at most we have to adhere to the industry standards. So let's see that how these requirements are how these requirements and the issues we can mitigate using the mitigate using the uh, mitigate using the requirement toolbox. So before we go for that, most of the system engineers, when they are developing the design, they face three major issues: that either the requirements are stored separately and the modeling or the design work is going completely different. So they can't actually trace the things and make sure how the progress is moving. Linking is most of the time the tedious part. So the requirement toolbox helps you to import all these external requirements into the model-based design approach of the Simulink, and you can create your own requirement model. And moving forward, you can link this complete model with the various subcomponents that you are building with using the Simulink and MATLAB, and make sure that all of your requirements are meeting. And you can also link all these requirements to various tests and generated the code. So you should be this actually gives you capabilities to analyze how your requirements are implemented and verified throughout the system. Are there requirements has any issues, or relieving the requirements can get you the better results? So all these analysis you can do. And finally, you can generate the requirements reports for the review and certification submission. So moving forward, there are a lot of capabilities that requirement toolbox can do. So we have a short video here which explains more about the requirement toolbox. Let's have a
Requirements
check.
Toolbox lets you author, link, and validate requirements within MATLAB or Simulink.
Uh, Gwen, can you confirm if this video has audio?
Yes, the audio is working.
Okay, fine. Thank you.
track their implementation and verification status, and quickly respond to requirements changes. Requirements from external sources can be imported and viewed within your development environment. You can exchange data with other tools using an industry standard interchange format. You can formalize requirements with a requirements block and validate they are correct. You can manage requirements directly within Simulink, System Composer, and Stateflow. Traceability to designs can be quickly created through drag and drop. Badges indicate where links exist in the model, and you can show requirements content directly in the diagram without modifying the model. Navigate directly to related design elements with traceability links. If you select a requirement, its related design elements are highlighted, and if you click a block, the linked requirements come into focus. You can also link requirements to test cases to track their verification status. The implementation and verification statuses show the completeness of designs and related tests. To review traceability between artifacts, use the traceability matrix. You can directly create links where there are gaps. When a linked requirement or test changes, you are notified so that you can determine the impact of the change. You can visualize upstream and downstream artifacts using the traceability diagram. Establishing full lifecycle traceability enables you to document your requirements are being met, understand the impact of any changes, and create a digital thread between requirements, MATLAB code, designs, generated code, and test cases.
So yeah, if we summarize all the capabilities of the requirement toolbox, you can actually author and organize requirements with the requirement editors. You can integrate third-party requirement tools, either it's IBM tools or your Word file or Excel file, where all of your requirements are mentioned. Moving forward, you throughout your design process, you work with requirements and design together. So always you know that your components and subsystem or system, how do they need to function, or if there is any special impact is coming on the component level because of a particular requirement. Uh, Also, it gives you an opportunity to continuously analyze your requirements coverage, which requirements you met, which requirements are verified, or which requirements are still an issue. And depending on that, you can add also the comments and justifications for them. Uh, it gives you an opportunity to, it gives you a benefit of identifying the change impact. So you are not worried about what is making what change, either how the requirements are impact from the subcomponents, or the component design is affected by requirements. And finally, it gives you the various reports that you can generate, which you can use for review and your submissions. Moving forward to system architecture, once your requirements are finalized, we need to develop the system architecture. At the system architecture level, still you may be at the design cycle where you are not developing the complete design models, subcomponents, but you know that what each system would be able to do, or what each subsystem should be able to do. So connecting these requirements to the subsystems can give you at very high level the idea that what can be your subsystem level requirements or the component requirements which you need to build and you need to take care for the integration. So this let's see it with a short video on the system composer, which helps us to develop the system architecture and link requirements.
System Composer is a model-based systems engineering tool for system and software architecture design, allowing you to decompose complex systems or a system of systems into smaller, more manageable pieces. This easy-to-use tool bridges the gap between high-level requirements and low-level algorithm and simulation workflows, allowing for scalable specification and analysis of system and software architectures. The tool lets you author and edit architectures, link requirements to architecture and test cases, and define custom properties of architectural elements. With System Composer, you can generate new views of the model to gain insights into functional flows, component dependencies, and more. You can also edit those views directly. You can define software architectures from built-in templates that are generic or specific, like AutoZar Classic and Adaptive. You can even model the behavior using various formalisms, such as block diagrams, state charts, and sequence diagrams. Another feature of System Composer is the ability to allocate or establish relationships between elements of different architecture models, which may represent different abstractions of a system, such as functional decomposition and logical or physical architectures. And of course, you can seamlessly integrate with Simulink, FMUs, legacy code, and more for traceability and continuity from MBSE concept through model-based design and verification. System Composer.
So to summarize the video, the System Composer gives you the capabilities to author your architecture and associate various architecture models to your requirements, adding the custom properties to them, doing architecture allocation to various requirements. You can also do the behavior modeling, and finally, you can implement all these requirements with the component and system level, at component level and system level of model-based design. So once your systems are ready, your system architecture is ready, we move forward for the component design. And the component design may include various systems, various subsystems. It may be your propulsion devices. It may be your flight controller software, flight controller hardware, or it may be the autonomous algorithm that you are going to develop. So there are multiple tools are there which actually helps you to do all of these. And for moving to the system to the components, we have specifically a multiple libraries which helps you to utilize first principle and perform data-driven modeling in Simulink. You can perform dynamic simulations to evaluate and refine your system performance, and all of these comes with a lot of available blocks specific to libraries. So we are going to talk about such specific libraries, what we call as block sets and toolbox in Simulink. So with Aerospace block set, you can model your vehicle components, you can bring your environment models, you can actually, with these environment models, you can model your gravity, various environmental parameters such as density, temperature, pressure, airspeed. Moving forward, you can also perform your, at system level, you can perform your aircraft controls and stability analysis, which helps you to develop your flight control system. You can perform your complete complete mission simulation, and you can do your flight visualizations to assess how is the dynamic performance of your flight vehicle. You can also analyze your complete flight and mission. So for depending on your mission simulation, depending on your missions, you can do your various flight and mission analysis. And for all these purposes, we have many ready to simulate examples based on electric aircraft and jet aircraft. So these ready to simulate examples gives you a direct opportunity to work to bring various subsystems and customize your data and overall model your flight vehicles. Specifically interested to UAVs, the UAV toolbox provides the capabilities to uh, develop your UAV algorithms, UAV autonomy algorithms, MAVLink connectivity to make sure that various subsystems are working fine. This MAVLink connectivity in case of your vehicles can be changed with the various communication modes, wireless communication modes, and you can also bring your vehicle flight data and you can analyze them with the UAV flight log analyzer app. We also have support for the controller deployment and testing, especially for PX4 flight controller software stack. So if you're working around the PX4 flight controller software stack, you can directly do the modeling and integrate, you can directly do the modeling of your flight controller Simulink and integrate your code with the existing PX4 stack in the software. We do have a ready to use examples such as design and tune controllers for VTOL UAVs and implementing a multi-rotor UAV, which includes a rotorcraft for a package delivery mission. Uh, if you are going to work around the computer vision system using the computer vision toolbox, you can automate your image and ground truth, you can automate image and video ground truth labeling. You can develop various deep learning and machine learning models and implement with the computer vision toolbox. Uh, there are opportunities for the camera calibration so that you make sure that your hardware and the camera hardware and the software views are aligning. You can use also the LiDAR and 3D point cloud processing and multi-object tracking capabilities as well. Moving forward, there is a deep learning. You can use the deep learning toolbox to generate deep learning toolbox to design your own deep learning network and integrate with you can design your own deep learning network and analyze its performance. You can also integrate it with the existing models such as PyTorch and TensorFlow. We have Deep Network Designer app, which actually is this complete workflow. And at last, you can generate and deploy optimized C or C++ and CUDA code for your hardwares. So you don't need to worry about how the algorithm is designed or how your deep learning models are designed. You can take care of their models, designing model, and then at last, finally, you can generate the codes for them. Right. And once we are done with the once you are done with the component design, the next phase comes for the component implementation, integration, and system integration. So this phase mostly involves developing your code and deploying it on hardware. So with MATLAB and Simulink, we do have capabilities where you can deploy to the target with zero error codes, and this support is available for various FPGA hardwares, NVIDIA GPUs, and other CPU hardwares as well. So the opportunity for this is that this develop all the optimized code, and there are optimization libraries are available. So for example, if you're working with the on the Intel CPUs or ARM Cortex CPUs, then or NVIDIA GPUs, you may be interested to run the optimization library based code for specifically for these hardwares. You can do this along with the modeling, and if required, you can generate library free source code, which actually increase the overall system performance of your code. So we do have a simple demo on how can you develop the code from a Simulink model. So using the Simulink order, you can develop the code for your complete system. So here we see that we are going to develop a code for a jet engine blade model that we is developed, and you go for the you select some of the modes and optimization parameters that you want to go for, and with click of buttons you can develop this code. The good thing is when you are developing this code, you can make sure that it's based on industry standards, and also this complete C++ code is generated along with the report. So through the report, you can analyze how your code is going to perform. Once your code is developed, you go for a deployment either for the SIL simulations or for the HIL simulation. So let's understand just with a small architecture that how it can go completely for a hardware in the loop simulation system. So consider this simple Simulink model where we have the high fidelity jet engine turbine plate data which has been modeled, and we are trying to develop a controller for nonlinear models. So here we need to generate the code for testing this. We need to generate the code for flight controller algorithms separately, and we need to test it against hardware. So what you can do is this controller code can go in your target platform, which can continuously work with your real-time computers such as speed code, and on these real-time devices, you can generate the code for your plant model, and you can test your hardware in the loop simulation capabilities. Yeah. And finally, we move for the system test and verification, which is one of the final stage of our design cycle. Along with these design cycles, if we talk, because with the model-based design approach, we are analyzing our architecture development since starting, and we are making sure that we are meeting all the requirements as standards with the dynamic simulation and analysis tools. All the formal verification capabilities are performed, and you can also reuse the test cases. So there are multiple tools are available which helps you to do this, including your requirement toolbox, Simulink Design Verifier, Simulink Test, Polyspace Bug Finder, Polyspace Code. So all these are part of the model-based design approach with Simulink. And there is one more user story where the Alina Ermaki develops autopilot software for DO178, DO178B certification, and they did it completely with the Simulink past model-based design approach, and they could cut down the overall project period by a long time and save a lot also on their resources. So you would be curious that all these uh, all these tools we discussed during the webinar, you may be new to them and you want to learn more. So if you are for that purpose, we do have a lot of on-ramps are available. So on-ramps are available where you can start your journey with learning about MATLAB and Simulink, System Composer, Requirement Toolbox, and along with there's a lot of videos are available at the mathworks.com, along with the detailed documentation on how to use each toolbox and what are its capabilities, along with the uh, along with a number of examples. So you can use all these resources uh, to uh, to start your journey for the model-based design approach. We have also curated this uh, GoAERO page, especially dedicated for the GoAERO competition. It includes all the learning resources you require, and you can also request for the complimentary software license here. So all the tools and all the tools that you require for the GoAERO competition for the model-based design approach are given as a part of our sponsorship to this competition to all the team. So you can just come here and click. And also, if you have any queries, you can reach out to us at roboticsarena@mathworks.com. Thank you.
Thank you.
That's all from my side.
Great. Thank you so much, Khushin. If there are any questions, we're happy to take them. Please post them in the Q&A feature in the Zoom. As always, a recording of the lecture will be available so that you can review all of these details. And we will be providing more information about how GoAERO teams will be able to access all of these resources in stage 2 of the competition. In the meantime, just a few reminders. If you're not already registered on the website, it's herox.com/GoAERO. Please review all of the details and the timeline information. As you know, the deadline is approaching on December 11th for the stage 1 submission. If you have not already started, we encourage you to do so quickly. You'll find that you can, once you're registered, you can see the full submission form once you click on Begin Entry. You'll also find that you can see a PDF version of the submission form in the Documents tab on the website so that you can work offline and you understand all of the formatting requirements for your technical paper as well as for all of your uploads. We'll also note that we've answered a number of questions from people regarding the stage 1 submission, both in the forum and via the FAQs. So if you do have questions, we encourage you to also explore there in case your question can be responded to. If not, please utilize the forum to post any questions that you might have. So if there are no questions for Khushin at this point, thank you so much for your time. We really appreciate it. We really look forward to this incredible resource and the information that you have for our teams as they begin working on their prototypes for stage 2. And we're really excited about all of the resources and possibilities that your simulations can provide as teams are testing out their devices. Thank you so much.
Thanks a lot. And just one information I would like to share that we would be
Yes.
sharing this slide deck with you that you can share with the teams. So all the links and all the tools what we discussed during the webinar would be easily accessible to the all the participants.
Great. Thank you so much. We really appreciate that. We'll certainly add the link as we post the
Yeah.
recording so that people can easily find the resource. Thank you so much, Khushin. Take care.
Thanks a lot. Take care.
Bye.